Network layer protocols and IP addressing.
IP version 4 addresses. There are two different versions of IP addresses, version 4 and version 6. Everything we are talking about in this course, apart from one chapter, is about IP version 4. Version 6 will have just one chapter, and that chapter is called IPv6. So let us introduce these addresses and become a little bit more comfortable with them. We've been using them, we've been configuring them, we have been talking about them, but what exactly do they mean? That is the purpose of this part of the class. So what is an IP address? And we are saying that an IP address identifies a node or an interface on a network device. Now, I need to clear this right from the beginning. When we say a node here, we are not saying your laptop or my server or my laptop or my PC or whatever router device, router. What we mean is the interface on that device. It can be the interface on a router. It can be a virtual interface on a switch. It can be an interface on a firewall. It can be an interface on a PC. It can be an interface on a phone. It is the interface, but not the phone. So sometimes you find a phone has more than 2 network interface cards, NICs. Each of these network interface cards will have an identifying IP address. IP addresses are the ones we use to forward packets on the network. So normally we have a number of devices on the network. As you can see, there are quite many devices. An IP address is the special identifier for each of these devices on a network. When these devices are on one local area network, meaning they are reachable in the local area, they have to have unique IP addresses, each of them. This device cannot have the same IP address as this one, as there is going to be an error called the IP conflict on the network. They need to be different IP addresses. So now, if we happen to have a total of 4 billion IP addresses, it means with our 4 billion IP addresses, we are able to only use 4 billion IP addresses minus 2, because one of the IP addresses will be used for the name of the network, and one is a special IP address that we use if we want to send traffic to everyone in that network. But again, this is quite a very, very big network, as we are going to see, and we want to reduce the sizes of our networks accordingly. Again, an IP address identifies a node on the network and not the device. We use it to find the destination for the data. If we are using IP, this is not the only routed protocol. But if we are using IP and a user wants to connect a computer to the network or to the internet for that matter, that user needs to apply for an IP address. We are going to see in this particular class that that IP address is, in this case, the public IP address. The IP address will identify the node on the network, and we use it to find the destination of the data that we want to forward. We also use IP addresses to implement global network communication. An IP address is an attribute of a network interface. It is an attribute of a network interface and not a network device. If we want to assign an IP address to a device, we are actually assigning an IP address to an interface on that device. I'm repeating that several times because I've made cases where it causes several levels of confusion. The interface that needs to use the IP address is usually the interface of a computer or a router, as far as this class is concerned. But as I've mentioned, we have virtual interfaces on switches, we have phones, we have firewalls, we have several devices that we use even in the virtualized realm that use IP addresses. So I'm sure you have all seen these IP addresses like 192.168.1.7. When you check your network configurations right now, you'll find it has some IP address. Maybe something that looks like this, or something that looks like 10.10.1.6, something that looks like that. What are these 10.10.1? Why do we have dots? What is 192.168.1.7? Why are we not seeing anything like 127.11.11.16? Why are we never seeing this? Why do we keep using 127.0.0.1 for localhost? If you have not used it, I'm sorry, ignore. But why do we keep using this in programming realm, in database realm, in website hosting realm? Why do we keep using this IP? Wow, how do we write an IP address? What do we need to know about IP address notation? Now, first off, an IP address is 32 bits long. 32 bits means that we write 32 zeros or 32 ones or 32 digits that contain zeros and ones. So it can be 0, 32 times. It can be 1 32 times. It can be a mixture of these 1 32 times. They are 32 bits. They are 32 bits in an IP address, zeros and ones in an IP address. They could be all zeros, they could be all ones, they could be a mixture of zeros and ones. And let me mention this right at this stage. If they are all zeros, this is the very, very first IP address in the entire IP address range. If they are all ones, this is the very, very last IP address in the entire IP address range. This IP address is supposed to be called the network address, but we don't call this one the network address because of how special it is. This one is supposed to be called the broadcast address because it is the last in the network, but because this particular one is the limited broadcast, it is the last broadcast of all broadcasts, we don't entirely refer to it as just broadcast address. We're going to come to that. Now, everything between the network address and the broadcast address is the IP addresses we can assign to hosts on our network. That is so important, and we are going to continue seeing it in this session. Now, as you can imagine, if we have an IP like 0100110110010100110001000100 32 times, it is very difficult for us to cram this figure. Any of you who is okay with this, you would like to be writing this every time you configure your computer's IP address? I'm sure there is none, because it is messy, it is disorganized, it's hard to internalize. So we get a better way of representing this. We start representing it in decimal notation, But again, writing a number such as this in decimal notation could be very tricky. Precisely, the number is 4,200,000,000 something thousand something something. This is how big the number is. It is boring. It is so big. It's complex. We do not want to be dealing with things like this. The human brain is knowledgeable about dealing with a large number of small things than a very big one thing. So we break this down into octets. Instead of 32 bits written once, we want to write them in groups of 8, something like 11000000. Those are 8, 1110101000. Those are 8, 11001010. Those are 8, 11000001. Those are 8, giving us a total of 32 still. But now that we write them as octets, every octet can be mapped to a number between 0 and 255, giving us 256 possible mappings. Each octet can be mapped to a number between 0 and 255. Each octet can be mapped to a number between 0 and 255. Each octet can be mapped to a number between 0 and 255. When we do this, our IP address is a lot readable now. So we can write the whole of this as just 192, put a dot, that's the first octet, write this as just 168, put another dot, that's another octet, write this as just 10, put another dot, that's another octet, write this as just 1. But this, in fact, was 32 bits in size that we have written as dotted decimal notation. So they are dotted decimal numbers. So we typically write our IP address in dotted decimal notation, but the IP address itself is 32 bits in size, is a binary. Keep that in your mind. An IP address is a binary number, and those IP addresses range from 0,0,0,0,032 times, which you write in dotted decimal like this, 0.0.0.0. In fact, right here there are 8 binary zeros. Here there are 8 binary zeros, 8 binary zeros, 8 binary zeros. That's the very first IP address. And the very last IP address is 255, These are 8 binary ones, .255, another 8 binary ones, .255, another 8 binary ones, .255, another 8 binary ones. This is the IPv4 address range. If you want to know how many IP addresses we have in total from IPv4, we get 256 times 256 times 256 times 256. And then someone asks the question, why are you saying 256 if we are seeing 255? Yes, we are seeing 255, but we started counting from 0. So if you count 0, 1, 2, 3, 4, 5, and so on up to 255, you will actually have done 256 counts. So there are actually 256 numbers counting starting from 0. Now, because I'm talking about IPv4 being binary, that we are converting to decimal, it's very important that we get comfortable with this conversion. And this is why it's going to become interesting, because we all know how to convert binary to decimal using the several methods we have learned and the ones we have invented. We all have some very fast way to do this, so I don't want to force this on you. But this slide has a very nice way of converting this that I love, I like it. You start by, all you need is this table. This one here, which is 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5, 2 power 6, 2 power 7. But don't worry about this, just worry about the results. The results are 1, then multiply 1 by 2 to get the next one, 2, multiply 2 by 2 to get the next one, 4, multiply 4 by 2 to get the next one, 8, multiply 8 by 2 to get the next one, 16, multiply 16 by 2 to get the next one, 32, multiply 32 by 2 to get the next one, 64, multiply this by 2 to get the next one, 128. Once you have these 8 numbers, you're done with your conversion. Just get whichever binary you want and superimpose it on these 8 numbers. This is 1, 1, 0, 0, 0, 0, 0, 0. After doing that, what you do, you add together those numbers that are mapped to ones. In this case, it is only 128 and 64. Now, when you do 128 and 64, add them together, you get 192. Because all these others are 0, this number in binary is 192. It's that simple, right? Let's try that again. So let us convert this into decimal and see whether it becomes 168. Again, just get hold of your numbers, 128, 64, 32, 16, 8, 4, 2, 1, and superimpose your binary digit octet onto these. This one is 1, 0, 1, 0, 1, 0, 0, 0. And what you do, let me do that again, 1, 0, 1, 0, 1, 0, 0, 0. What you do, you add together all the digits that are mapped to a 1. So we are going to get this 128, add it to this 32, add it to this 8. That's going to be our number in binary. So get this plus 8, get 40. 40 plus 128 gives us 168. Anyone wants to try that? Anyone here? Anyone wants to convert this to decimal? Anyone wants to convert this for me to decimal?
Let me try.
Okay. Okay, okay. Okay. Everyone else can be trying. In fact, you can all try and post the answer in the Zoom chat. Let's see what people get. Post your answer in the Zoom chat after converting. Let's see what different people get here. Let me copy for you a bit. The numbers are 128, then 64, then 32, then 16, then 8. I just keep dividing by 2, then 4, then 2, then 1. What next? Superimpose your binary onto that. This is 1, 0, 1, 0, 0, 0, 1, 1. After that, add together those ones that are mapping to the 128, add that to 32, add that to 2, add that to 1. What do you have? What do you have? This gives us 160. This gives us 160, 163. Anyone got this? Oh, great, great, great. People already have that in the Zoom chat. Thank you. Thank you. So that is the conversion. That is the conversion. It's very, very easy. It's very, very, very easy. And the conversion reverse works the same way. If we have 179 and we want to convert it to binary, 179 and you want to convert it to binary, anyone else try this with me? Our numbers are 128, 64, 32, 16, 8, 4, 2, 1. But now what do? We don't have a binary to superimpose. So what we are going to do is to subtract these numbers here from this one by one. We start by subtracting it from here. 179, remove 128. What do you get? What do you get here? You get 51. Okay. Now the 128 gets a 1. We get a 1 on 128. Take this 51 in the next one. If it is less than that number, that one gets a 0. I hope that makes sense. So we move it to the next part. In other words, when you bring the 51 here, we cannot subtract 64 from it. So we get a 0 there. We take the 51 here. Can we subtract? Yes. Oh, 11. This gives a 9. This gives a 1. So that gets a 0. Every time we subtract, we get a 0 and move it to the next place. If we move the 19 here, we move the 19 here, subtract. Yes, we get 0, 3. That gets a 1. Move the 0, 3 here. We can't subtract. That scores a 0. Move the 3 here. We can't subtract. That scores a 0. Move the 3 here. Oh, we can subtract and we get 1. That gets a 1. Move the 1 here. We can subtract and get 0. That gets a 1. So our answer becomes 1, 0, 1, 1, 0, 0, 1, 1. This is 179 in binary. Oh, that's great. That's great. I shouldn't have got it. Shouldn't have got it right. Let us do one more. Let us subtract. Let us convert 254 to binary. Again, our chart has 128. Can anyone try this out as I do it? Anyone? Anyone? I'll be grateful. 128, 64, 32, 16, 8, 4, 2, 1. All right, let's see. So we first bring that here, 254. We subtract that. What we get? This 14, we get a 6. This 2, we get a 2. This is a 1, 126. We remain with 126. So we carry this 126 up there, 126, and subtract. Every time we can subtract, we go ahead and subtract. What we get here? 2, and 12 minus 6, we get 6. Then we carry this 62 right there, 62, and subtract. We can still subtract. Get a 0, get a 3. Oh, that's great. Move this 30 right there. Every time we subtract, that scores a 1. We subtract, that scores a 1. Now this is 30. We subtract. This is 14. That scores a 1. We move the 14 right there. We subtract 8. That scores a 6. Sorry, we get a 6. That scores 1. We subtract. We take the 6 here, we subtract 4, we get a 2, that score as a 1. We take the 2 here, we subtract 2, we get a 0, that score as a 1. We take the 0 here, we can't subtract. So this scores a 0. So our answer becomes 1, 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 6. Oh, what was that? Oh, beginning from here, this was 1. Excuse me.
Yeah.
Yes, 1, 0. Okay. Yes. We have people who have got it in the Zoom chat. Thanks a lot. Thank you a lot. So that is conversion from binary to decimal and decimal to binary. It's going to be important for any network engineering career, whether you like it or not, you know, unless you're going to use apps to do it. Yes, there are apps to do it, but you feel it fun if you do it yourself. All right. So that is an important aspect for us about the IP address notation. We write the IP address originally in 32 bits, but for readability, we convert that into 4 bytes. 4 bytes as 4 different octets: octet 1, octet 2, octet 3, octet 4, or dotted decimal notation. So let us dive a little bit deeper into this structure of an IP address and understand what exactly is 192, what is 168, what is 10, and what is 1. Now, there are 2 important parts to an IP address that I need you to understand. The very first part of an IP address is the network part. We know that these hosts we are trying to give IP addresses are getting IP addresses so that they can join a network. It is like going to a new community. When you get a telephone number in Uganda, it will have +256 to show that it's a Ugandan telephone number. When you get a telephone number in Kenya, it will have +254 to note that it's a Kenyan telephone number. When you get a telephone number in South Africa, it will have +6, I think 3 or something, to note that it's a South African number. There has to be something in the number to represent the community. As if this is not enough, when you are in Uganda, you need to have 77 or 78, these days even 76, to mean that you are in the MTN community. Does anyone get where I'm heading? If you're in Kenya, you need, I don't know, 7 what, forgive me. But yes, you need something to note that you're on Safaricom or you're on some other network. If you're in Uganda, you're going to need 75 or 70 or these days 74 to mean that you're on the Airtel community. Does anyone get where I'm heading? For IP addresses, in the number 192.168.1.7, there has to be a part that represents the network, and there has to be a part that represents the host. All right, let's see this. We could either divide this number like this to mean this is for the network and this represents the host. If we divide that number like that, it means we are getting the IP address in the format network.host.host.host. Is anyone with me? You guys are too quiet. I don't like classes like that.
Yes, John.
Eh?
Yes, we are with you.
You know, my network is bad. I might go offline and I think I'm still with people and I speak for 3 hours, you know. Please try to make comfortable the habit of unmuting and saying, yes, 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 we are together. It doesn't cost a lot. Alternatively, in the IP address 192.168.1.7, same IP address, right? Exactly same IP address. We can decide to divide it from here and say this part is for the network and this part is for the host, meaning that we have an IP address in the format network.network.host.host. Is anyone with me? Again,
Yes, John.
in the IP address 192.168.1.7, same IP address, we could decide to divide it from here and say the whole of this represents the network and only this one represents the host, which means we are having an IP address in the format network.network.network.host. Now, why is this very important? because it drives us to 3 different kinds of IP addresses. Let's see them. We can have an IP address where only 1 octet represents the network and the rest of the octets represent the host. I want to note one important thing about this type of IP addresses. They have too many hosts. Too many hosts in the same network. For example, we could have an IP address like 1.1.1.1, 1.2.2.2, 1.4.3.9, 1.1.4.1.9, 1.255.255.255. You see all these IP addresses? If they are in this format, they are all on the same network, as you can see. Can anyone see that?
Yes, John.
But now imagine these IP addresses, but in the format network.network.host.host. Let me see who is following. Who can tell me which of these are in the same network? Which of these are in the same network if they are in this format? Someone, do me a favor. Who can do that? If we are writing the format.
1.4.3.9.
Pardon?
Then 1.4.3.9, 1.4.1.1.
1.4.3.91. Perfect. Perfect. Who was that? That is Chinecherim.
Yes.
Oh, thanks. Because now you see the 2 octets are for the network. So only these 2 IP addresses have the 2 octets similar. These 2 are in the same network. If we are in that type of network. However, let us say these IP addresses are in the format network.network.network.host. Which of these IP addresses are in the same network? Let's see. Which of these IP addresses are in the same network?
None.
None. Perfect. None. Now all these hosts are on different networks. This host is on a different network from this host, on a different network from this host, on a different network from this host, on a different. So if we have one host here with IP address 1.1.1.1, and we say that this IP address is in the format network.network.network.network.host, excuse me, and we connect it to another host. This is host A. Listen to me carefully. You're going to like this. Host B has the IP address 1.1.2.2, and we say it has the format network.network.network.host. Do you think host A and host B are on the same network? Someone help me.
No.
No.
So they are not on the same network.
No, exactly. If any of you opened our enterprise network simulation platform right now and put here one PCA, another PCB here, and try to ping from this PC to this PC, it will tell you destination host unreachable because host A cannot find host B. They are on different networks because of the formats. Listen very carefully to this other part. Same thing. If we have host A and connect host A to host B, and we give host A the IP address 1.1.1.1 and say it is in the format network.network.host.host, and we give the host B the IP address 1.1.2.2, same as it had the other example, and say it is in the network the format network.network.host.host. Are they in the same network?
Yes.
Yes.
Perfect. Now you guys see where I'm going, right? I'm going to
Yeah.
like this class because now if we did this in any in our enterprise network simulation platform, or you got 2 laptops and connected them with a network cable, Ethernet cable, and gave these IP addresses and somehow managed to tell your laptop that you're in this format, you're in this format, your PC1 will be able to ping PC2. It will be reachable because they are in the same network. Now, ladies and gentlemen, for every time in your life you ever configure an IP address, that IP address is completely meaningless unless you tell it which format it is in. The way we write this in our computers is using what we call the subnet mask. You have seen this in computer configurations and notes, but you probably don't know why they write it the way they write it. Let me do this again. You've always seen things such as 192.168.1.4 and subnet mask 255. Who has seen this?
255.0.
You have all seen this, right?
I've seen it.
255 is for network. .network, .host. This is what you have told that computer. When you go to another one and you say its IP address is 192.168.1.16, and you say it is also 255 subnet mask .255.255.0, you have said this one is also in the format network.host. Now, sorry, if this is 2, excuse me, you will note that your laptop 1 will not be able to talk to laptop 2. Why? Because the networks are what?
Are not the same.
Are different.
Are different.
This one will need to be 1 also. Because of the subnet mask, I repeat, it is because of the subnet mask. So if you want to solve this problem in an actual network, where this is 2, and you want to solve the problem, you can either go and change this subnet mask to .0.0, they will communicate, or change this one to 1 and this one to 1, they will still communicate. You can use one of the two. Are we together?
Yes.
Yes. This is the job of that thing we call the subnet mask. It is a way we tell an IP address that these parts are the network and these parts are the host. Because every IP address needs to have those two parts, the network part and the host part. And we need to be able to tell it which part is the network part and which part is the host part. If we do not tell it which part is the network part and which part is the host part, that will not be an IP address. You want to try that? Go configure your laptop with an IP address and don't give it a subnet mask. It will not communicate. In fact, it has a tendency of generating its own subnet mask because it knows that it must have a subnet mask. Are we together?
Yes.
Yes, we're together.
Yes, John.
Any questions so far?
Yeah, I want to ask you a question.
Yes.
You mentioned that if we have 255.255.255.0 and 255.255.0.0, when we have the IP address to be .1 and the other one .2.some.
No. Wait a sec. 255.255.255.0 and 255.255.0.0. And then this is 192.168.1.4.
Yes. 192.168.2.16. Now you said with this they can communicate.
No, they can't.
No.
No. I said you would need to change this also to 0. We either change both of these to 0 or just change this one to 1.
Okay.
But let me explain why. Because this is a class, let me explain why they can't talk. Actually, if this is PC1 and this is PC2, and you come here and say ping, then you ping PC2. PC1 will successfully send a ping packet to PC2. The problem will be that PC2 is not able to send back a packet. Because with this subnet mask, listen to this very carefully, with this subnet mask, are we listening?
Yes, we are.
With this subnet mask, this IP address is also in that network. Are we together? So PC2 will see that ping 192.168.1.4. Ah, this guy is on my network. Are we together? So for him, he will send. And this guy will receive. But when he receives, he sees that it came from 192.168.2.16. Now he needs to send back. When he checks that IP address, according to his subnet mask, it is not on his network. So he will fail to send. Are we together?
Yes.
That is what will happen. If you ping and capture packets somewhere along the way, you will see that this guy is sending, but this one is not replying. One time, maybe if you remind me, we shall try that out practically in ENSP and see how it works. So let me do this again. An IP address is 32 bits long. It has two parts. It has the network part and also has the host part. How do we know which one is the network part, which one is the host part? We use the network mask or the subnet mask to know that. So how do we know that this one is the host part and this is the network part? It's because this subnet mask was 255.255.255.0. Are we together?
Yes, we are.
Yes. Now, another interesting thing I want to bring up, I want to keep bringing interesting things, is that when we write 255, we have said this can be written as 1111, isn't it?
Yes.
So 255.255.255.0. This can be written as 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. Anyone help me? Dot 1, 2, 3, 4, 5, 6, 7, 8. Dot 0, 0, 0, 0, 0, 0, 0, 0. Do we agree?
Yes.
Yes.
These are
Yes.
8 ones. These are also 8 ones. These are also 80 ones, isn't it?
Yes.
In other words, this is a subnet mask that has 24 what? Do we agree?
Yes, we agree.
If we have a subnet mask such as 255.255.0.0, this is 1, 2, 3, 4, 5, 6, 7, 8. Dot 1, 2, 3, 4, 5, 6, 7, 8. How many ones are those?
16.
16. This is a subnet mask that has 16 what?
1.
If we have a subnet mask 255.0.0.0, we can know that this subnet mask has how many ones?
8 ones.
8 ones. Perfect. As I said, I'm falling in love with this class. Let's see where this takes us. I think instead of writing 192.168.1.4 with subnet mask 255.255.255.0, we can just write it as 192.168.1.4 with a 24-bit mask.
Yes.
Yes. Why write all this? By the way, network engineers are typically very lazy people. They want to be a subnetting once and manage the enterprise network for 10 years, sitting, taking a cup of coffee every day. Only job they are doing is troubleshooting. We don't want to be writing this every time when we are planning. So we get a simpler way to write it. We can now write 192.168.1.16 with a 255. That's why you say I'm struggling to write 255.0. We can simply write it as 192. Someone help me. .168.1.16 slash what? Perfect. Now this is what we call the classless interdomain routing notation, normally pronounced as CIDR notation. This is what we call the classless interdomain routing notation, CIDR notation. This is the traditional one. Good luck with it. That's why you see that right here, instead of writing the entire that. So again, subnet mask is the special number that helps us know which part represents the network and which part represents the host. One other thing I want to stress about this, every person is from a certain community. An IP address is a number written in form of community.person. These can be 2 octets, 2 octets, 1 octet, 3 octets, 3 octets, 1 octet, it doesn't matter, but it is like that. One other thing I want to note is that if we have network.host.host.host, which we have said is 255.0.0.0, there are going to be too many hosts in one network. If we have network.network.host.host, which is like saying 255.255.0.0, we are going to have the same number of networks for the same number of hosts. If we have network.network.network.host, same as saying 255.255.255.0, we are going to have very many networks and fewer hosts in each network. This type is called class A. This type is called class B, and this one is called class C. So these things I'm telling you, people have already used them. They haven't given them names. We have class A addresses, class B addresses, class C addresses. So class A addresses are addresses in which the first octet is the one for the network. Okay? The first octet is for the network, and the remaining 3 octets are for the host. Are we together? A class B address is where the first octet and the second octet are both for the network. The remaining 2 octets are for the hosts. The third one is where the first octet, the second octet, and the third octet are for the network, and the remaining 1 is for the host. Let us do a quick calculation here, should we? Anyone ready with the calculator and you're fast at punching the figures? Anyone? Anyone? In a 255.0.0.0, we have one net octet that can go from 0 to 255. So this particular class A network, class A addresses support 256 networks. Now this one can go from 0 to 255. This one can go from 0 to 255. And this one can also go from 0 to 255. Meaning they are 256 times 256 times 256 possible hosts on each network. Are we together?
Yes.
So 256 networks, and each of them would have 16 million something hosts on it.
16,777,216.
216. Perfect. Perfect. Who was that?
Hope.
Oh, Hope. Even the name. See, this is the number of hosts on each single network. So we shall have 1.0.0.0 one host, 1.0.0.1, 1.0.0.2, 1.0.0.3, until this last one reaches 255. Then we shall go 1.0.1.0, 1.0.1.2 until 1.2, until this reaches 255. This will go to 2. This one reach 255. This will go to 1, and so on and so forth. We shall have a total of, Hope help me again, 16,777,000.
216.
Pardon?
216.
216. For the 1 dot, there will be those hosts. Then the 2 dot, there will be those hosts. Then the 3 dot, in the 3 octets remaining here, there will be those hosts. 4 dot, and you reach 255 dot, those hosts. So the very first address, I hope some of you are following with me, because this is going to get messy. The very first address will be 1.0.0.0, Who can tell me last address? 1 dot what?
1.255.
Uh-huh.
.255.
Uh-huh.
.55.
Perfect. I love you guys. So this is going to be called the broadcast address. It is a special address that we send packets to if we want everyone in this network to receive them. We want to force everyone on this network to receive those packets. We say ping 1.255.255.255. Everyone on this network, let me get to this. The first one is called the network address. The network address is the very first address in each range. So if we have 1.0.0.0/8, which is what that address was with its subnet mask, I told you it doesn't make meaning without a subnet mask. It will range from this up to 1.255 as I'm still practicing this name, as Chinecherom has told us. 1.255.255. It is the range. Everything in the middle here can be allocated, but these two cannot be allocated. Their network address, it becomes the name of the range, and broadcast address, the special address we send to if you want everyone in the range to receive a packet. Again, for every network like 1.0.0.0/8, we shall have 16,777 hosts, 777,216 hosts. When you go to the second network, 2.0.0.0/8, we shall have 16,777,216 hosts. The third network, 3.0.0.0/8, will have that same number of hosts. Oh, wait, the first network was actually 0.0.0.0/8. So we shall have these networks go up to 255, which gives us a total of 1, 2, 3, 4, 5, up to 256 networks. I wonder if anyone is following. This is important, very important if you have to capture subnetting. Now, let us think of the other type of IP addresses that have the format network.network.host.host, which we have said, according to this slide, are codenamed class B addresses. Let us say we have the network 172.16.0.0/16. /16. This is the network. Okay, this is the network. Now you notice that this will go from 0 to 255, giving us 256 possibilities. This one will go from 0 to 255, giving us 256 possibilities. So the networks can be a total of 256 times 256. Okay? Are we together?
Yes.
And how many hosts are there for each network? This goes from 0 to 255, giving 256. This goes from 0 to 255, giving 256. This is going to be 16. Oh, excuse me. It's going to be 65,000. Someone, hope, please, calculator. Oh, what do you get? 536. They are going to be 65,536 networks, and each of them will be having 65,536 hosts in it. Are we making sense?
Yes.
Perfect. Let us look at a typical class C address. It is in the format network.network.network.host. Hey, I'm going to ask an interesting question after all this time I'm saying all this nonsense. Network.network. So we have 192.168.17.0, and we are saying the subnet mask is 255.255.255.0, making it a class C, right?
Yes.
So we know that they are going to be up to 256 values here, then up to 256 values here, up to 256 values here. That's the network, giving us 256 times 256 times 256, giving us 16,777,216. 16 what? Networks. And each of those networks has only 256 host addresses. Hey, who is loving this? So I want you people to answer me a simple question. We all know how technology has been developing. Someone tell me, which of class A, class B, class C networks is most favorable for long ago, and which one is most favorable for today? Which one is most favorable for long ago? Which one is most favorable for today? Class A could support 256 networks, and each network could have 16,777,216 IP addresses in it. Class B could support 65,536 networks, and each network would have 65,536 hosts in it, or IP addresses in it. Class C can support 16,777,216 networks, and each network has 256 IP addresses in it. Which of these three is ideal for prehistory, long ago? Prehistory, long. Which one is better for long ago?
Long ago.
Let me see who is me.
A.
Why?
Because class A has fewer networks and more hosts.
Good.
And long ago, we had
in the days. Yes, I love your answer. In the days of then, we had very few technology companies. And those technology companies were extremely large. Companies like IBM, companies like Microsoft, few companies, but they were all large. They have very, very many users. So we want a network that can support extremely many users. Very few universities, but they were very large. Very, very large. So you want a university to have a network and all its users on that network long ago. This does not apply today. We still have these companies, yes, okay, they will need the class A, but we have more of small companies that have 200 employees, that have 100 employees, that have 250. They are mob, so class C works better. Does anyone see where I'm headed?
Yes.
But what's the problem? Class A, 16 million IP addresses in each network. Class B, 65,000 IP addresses in each network. Class C, 256 IP addresses in each network. Can anyone tell me which of these classes can support a mid-sized company in Uganda today? Which one?
Class C.
Class C, are you sure?
Mid-size.
Yes. Imagine you can only buy one network at a time. You can't buy less than one network. Your company has 20 employees. It has 90 employees. It has 110 employees. You go to buy and you have to buy the whole network of 256 IP addresses when you need only 90?
No.
Are you getting me? Is anyone getting me?
Yes.
Class A, Class B, Class C are all history. They don't apply to us anymore at all. We have companies of 5 employees and they want internet. They can't start using an entire 256 network address class C. It doesn't work. Even in companies where we have 300 employees, these days we have divided them into finance, sales, technical, what, all that nonsense companies keep calling. And every day they're coming with new terms. And they want each of the departments on a different network. So you will find, yes, the company has 300 employees, but the biggest single network they have is only maybe 50 employees. So they have 50 and 50, then luggage carriers, 50, secretaries, then managers 16, then what? They don't need one network of 300 addresses. Is anyone getting me?
Yes.
That problem became a big problem, and we are going to address it using subnetting. But before that, we have just a simple calculation of the same things I've been showing you here. Right? In this case, we have that network with that subnet mask, and we want to be able to identify the network address, the very first address, the broadcast address, the very last address, and the number of addresses in between. So the first thing we need to do is to see the subnet mask. That subnet mask is saying it has 16 ones, 8 ones, and 8 ones. That's the subnet mask. And then convert the address itself to binary. 172, we convert it to that. 16, we convert it to that. The 10, we convert it to that. And the 1, we convert it to that. After that, we perform the process we call ANDing. This is the process the computer does to know the destination IP address on its network. It starts comparing bit by bit that if both are ones, the result is a what? A 1. If one of them is a 0, the result is a what? A 0.
0.
So let me hide these 3. Don't look at them. Okay? Shinta, are you there? Shinta, kindly unmute.
Yes.
Yes, Shinta. What do we get here when we add?
A 0.
A 0. Perfect. Thank you. Derek, are you there? Derek, kindly unmute. Derek. Now Derek is going to say his network is down. Okay, Alex. Alex, you're there? Alex?
Yes, I'm here.
Yes, Alex.
Yes, I'm here.
Alex, Harriet will come next. Alex, what do you get when you add these two?
We get a 0.
A 0, perfect. Harriet?
MH.
What do we get when we add these two? Harriet? Harriet? Ah, you've disappeared. Sharon, what do we get when you add these two? All right, maybe they have network issues. When we have a 1 and a 0, we get a 0. As long as one of them is a 0, we get a 0. We only get a 1 when both of them are 1s. Now, when we perform that ANDing for each of the bits, what we get is the network address. What we get is the network address, convert it back to decimal, and we get the network address. This is the very first address in that network, and it has a special name, network address. We don't allocate it to any host in that network. The very last address is got by simply converting all the host bits to 1s. 255.255 is the broadcast address. Is anyone confused with this?
No.
I'm going to show you something as a bonus. All right? It's not exactly in the scope of this class, but it's very good to know practically. A bonus just for you. Just give me 2 minutes. I pick up my boss's call. I come and show you a bonus. right. All right, thank you. Thank you, thank you. This is only going to be understood by those who want to get their hands dirty with this stuff. All right, so let us say we have PC1 here, and we have PC2 here, and they are connected through a switch. If you don't know what a switch is, do not worry about it. Like that and like that. And let us say this PC has been given the address 192.168.1.7. And this PC has been given the address 192.168.3.30. This is a /24, and this is a /24. And you came here on PC1. You came here on PC1 and you say ping 192.168.3.30. Do you think your ping will be successful?
It will not.
It will not.
It will not.
Okay, because we have attended this class and I've said all my nonsense, and now we can all see that because of the /24, this network is different from this network, isn't it?
Yes, John.
Yes?
I have a question. I didn't understand what is in between PC1 and PC2.
It's a switch.
Okay, thank you very much.
It's a switch. Sorry about that.
Okay.
Switch A. So we are saying, because this is a /24, it is in the format network.network.network.host. This is also in the format of network.network.network.host. But the three octets are not the same. So the pieces are on different networks. We can see that. But of course your laptop can't see that, can it?
It cannot.
It can't. So how does it know that this IP address is not on my network? I told you it's a bonus. How does it know? Because it's not outside my monitor to say, I see this network, what is different? It isn't. How does it know? Let me answer, for purpose of time. This PC is going to perform the process called ANDing. Remember, PCs are very good with zeros and ones. So it is going to convert this into binary. Let me convert it real quick. That one is 11.000.000.000.000000111. This is this one in binary. And it also converts its own subnet mask to binary. 1111111111.111111.0000000. Are we together? And it will start ANDing. Of course, the computer will do this in microseconds. It will find a 1 here. Are we together?
Yes.
A 1. Can someone go with me?
A 0.
A 0.
A 0.
0.
0.
0. 0. 0. Dot.
1.
0.
1.
Are you guys reading what I've written or telling me what to write?
0. 1.
0, 1,
0.
0, 0,
Then
0,
All 0 and 1 at the last.
all zeros and the last one. And this one is all zeros.
All zeros.
Perfect. Let's convert this back to binary, to decimal. This is 192. Dot. This is 128 plus 32 is 160, plus 8 is 168. This is all zeros, dot 1. This is all zeros through, dot 0, slash 24. This is, the PC will do that and know that it is on this network. Are we together? After that, listen carefully, after that, it will add the destination IP address that you want to ping, because you say ping this and it saw this IP address. Now it will add this IP address against its own subnet mask to see whether it gets the same network. Are we together?
Yes.
If it gets different networks, it means that is not my network. It won't communicate. If it gets the same network, that's my network, it will send the packets. Are we together? Is anyone getting me? I don't want to talk about this that not even part of this class when no one is getting it. Can we just go to the next slide and do what is in this class? Or does someone want to know what the PC will get?
It's okay, let's move on.
Let us see. The PC will get the destination IP address, which is now the IP address of PC2, and add it with its own subnet mask. So the IP address of PC2 was 192.168.3.30. It will change this to binary, and it will get 11.000.1010. That is 128 plus that is 160, and then 8.000. Dot 3 is 0.000.00, turn on 2 and turn on 1, making it 3. 30 is 0.0.0. This is 128.64.32. Then turn on 16. Turn on 16. Turn on also 8. That makes 24. Yes.
And turn on 4.
Turn on 4, making 28. Turn on 1, making 30. 0. Are we together?
Yes.
And then its own subnet mask, PC1 subnet mask was all 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Others are zeros. And then it will add these two. It wants to know, is this guy on my network? It will get 1, 1, all zeros. 101.000.000011.0000000. Let's get this to decimal. 192 from here. Dot 168 from there. Dot 3. Dot 0. Was it the same as that of PC1?
Oh.
Now PC2 knows that guy is not on my network and it won't send packets.
Yeah.
Anyone lost? Anyone with a question so far? Let me do this for you. Let me do this. I'm going to get PC1 right here and PC2 right here. And I'm going to get a switch in the middle. And I'm going to connect these two using copper cables. Connected PC1 to gigabit ethernet 001 and PC2 to gigabit ethernet 002. PC2 to gigabit ethernet 002. And then I'm going to start up this topology. If anyone has a question at this stage, please feel free to ask as I finish this up. I'm going to give this an IP address. I'm going to call it PC1 here. I'm going to give it the IP address 192.168.1.4 with subnet mask 255.255.255.0. That's /24. I'll say apply and close. I'll open the PC2, give it its name, PC2, and also give it the IP address 192.168.3.30 and the subnet mask 255.255.255.0. And what I want to do is to get on PC1 command line interface and ping PC2 192.168.3.30. Now I have a typo here. Get rid of it and hit enter. Anyone can read this? Destination host unreachable.
Unreachable, yes.
Unreachable. Why? Because PC1 has done ANDing and seen that this destination is not on his network. He doesn't even waste time sending anything. Let me show you. I'm going to capture packets at this point. I'm going to be there watching whether anything gets out. I want to show you this. I want you to see that these things are not in theory. They are things that are happening out there in the world. Okay? Let me put this aside. I want to bring this here. Let me reduce this. I have space to watch the packets. I don't want to update. These things are cracked illegal software. If I update, they are going to get me. Okay, so this is my packet capture. Oh, excuse me. Excuse me. My packet capture is here. My packet capture is here. And my window for pinging is here. So let's see. When I ping again, you see? I wonder if anyone is following with me. You see, PC1 did not send anything at all. At all. You see, nothing has come here. At all. Let me change this to some IP address. Oh, sorry. Sorry, not that. Let me try to ping some IP address that is on the same network with PC1. I'm going to ping 192.168.1.10. Now we all know there is no PC with this IP address, right?
Yes.
It's not there in our network, but let me ping it and we see. Ping. Do you see this? Do you see this? PC1 sends a question. It's called an app request. Saying, hey, anyone called 192.168.1.10, please tell me. Before it sends the ping out, it sends an app request. If you're known by this name, please let me know. But no one is replying, so he doesn't send the ping. But you see that he has at least tried to find out who this is because he can see he's in the same community with him. Does this make any sense?
Yes.
But if we ping .3.30, he doesn't even ask. Do you notice that? Because he did ANDing internally, and so this is not on my network. I should not waste this person's cables. He's not on, he will not even send it out. I'm standing here capturing. If I ping another IP address on PC1's network, but it's not on our network, he will at least send a question. You see, I sent again. Hey guys, anyone with this IP address, please tell me I have information for you. He's sending 5 times. Please, I have information for you. Anyone on this IP address, I have urgent information for you, but no one is replying. Now let us change this to a network that PC1 can reach. .1.30, apply, And then we actually go to PC1 and now ping that one. 30. Enter. You see?
Yeah. Reply.
Anyone see that? Let me pause this and explain this. You see? He starts by asking, who has .1.30? Please tell me .1.4. And then look here, the magic of networking. The other PC, the other side says, you're asking for .1.30, that is me, and this is my MAC address. You see? So it tells him, that is me, and this is my MAC address. This is called an APP request. This is called an APP reply. Now, when PC1 sees the MAC address, this is the physical address, we shall see that in coming chapters, he can now send your message. Your message was an ICMP echo request. And PC2 sends this reply as an ICMP echo reply. PC1 sends another one, sends 5 times just to confirm. PC2 is actually there, he's actually ready to listen. He will always ask first, who is this? But you see up here, he was asking and no one was answering because there was no 1.10. This is ARP, and we shall talk about more of it when we come to ARP, because it even helps us to determine that there is a duplicate IP address on the network. It is a very, very important, indispensable protocol. We shall come to that. Again, I just wanted to confirm to you that if we ping an address that is not on our network, the PC will do internal ANDing, and once it discovers that, it won't even send out anything. It won't. But if it finds it is on its network, at least it will attempt to reach out. It will attempt to reach out and see, oh, okay, it seems I can't reach him. Let me try to reach him again. Oh, I can't reach him. Every time he tries to send an app request, an address resolution protocol request, he wants to get the MAC address associated with the IP address he's trying to talk to. Once he gets that MAC address, he knows he's on the physical link and he can send the packet that the boss wants to send. So this is how it works. Ladies and gentlemen, let's get rid of this and get back to our slides. We shall do more of this as we go on. So there is a quick quiz here. You're expected to calculate these 3 things: the network address, the broadcast address, and number of available addresses. Notice that for the network address, we just do ANDing of the IP address with the subnet mask. For the broadcast address, we just convert all the host bits to 1s. For the total number of addresses, we just make 2 to the power number of host bits. Which number of host bits is 32 minus the mask length? Are we together? The available addresses is this one minus 2. Why do we subtract 2 again? Because we want to remove the network address and the broadcast address. Again, we talk about public IP addresses and private IP addresses. Because these addresses were being used up, we have about 4 billion addresses, 200 something addresses in total, and they were being used up. So we split them up into what we call private addresses and public addresses. Public addresses are the ones we route on the internet. Private addresses are used internally in your private local area network. So for our very addresses, we saw class A, class B, class C. There is actually class D also and class E. Class D is for multicasts, which are not in the scope of this class, and class E are experimental addresses. You won't see them anywhere experimenting unless you go to study things like internal operation principles of routing protocols and so on, where you might use those IP addresses trying to experiment or confirm your theories and other things. But in network engineering, you're not going to find them anywhere actively being used. But class D addresses, you'll find them if at any point you decide to upgrade your certification HCIP, you might meet me somewhere and I'll talk about multicast addresses and you'll find lots of them there. But again, we are going to talk about the range of 224, multicast, the one that we use for OSPF, DR, and BDR, and others as we come to that point in this class. But multicast as an entire range, we are not going to talk about it because this class does not cover this. This HCIA does not cover multicast communication. So Private IP addresses are to be used internal to your network, meaning they can be repeated. Those ones used in Chambogo University can be used in Makerere University again, then used in MUBS again, then used in Lira University again, then they can be used several times, because every time any of these addresses needs to access the public internet, it will need to be translated using NAT, network address translation, into a public address that can be routed on the internet. So on the internet, public addresses cannot reach. Private addresses cannot reach, only public addresses can reach. Technically, they actually can, but ISPs are required by their regional internet registrars to block all private addresses. We call them the 1918 addresses, to block all of them from internet access so that we don't have traffic misdirection over the internet. So Class A addresses we saw begin from 1.0.0.0 up to 127. Actually, technically, it's 126.255.25 because 127, the entire range is a loopback range up to there. So from 1.0.0.0 up to 126.255.255.255, those ones are Class A. Out of this whole range, we select 10.0.0.0 up to 10.255.255. We select 10.0.0.0/8 and use it for private networks. So you'll find in Makerere University computers in this network. You will find in Chambogo University computers in this network. You will find in another big university computers in this network. In IU computers in this network. Probably Kabale University computers in this network. Where University computer, ETC University computer. They are repeated because they are behind core routers. They are not accessing the internet. If people in Makerere University try to access the internet, we shall deploy network address translation here to convert that address into a public address so that you can speak to the internet. We shall talk about network address translation. We shall even configure network address translation in this class, and you see how it works in ENSP, and you'll feel nice about it. And you will know why when you access my website, when you access another company's website, they will not see the IP address of your computer, but they will see the IP address in front of your router, what you call Easy IP implementation by Huawei. It's called NAT, Easy IP. We are going to look at it in this class. Why on the internet you'll never see this IP address? It is a private IP address. It only stops in your lab or in your office. It never goes to the internet. Some router is translating that address, that network address, into another address that will be routed on the internet. So when you say on your computer, ping 8.8.8.8, the 8.8.8.8 server, Google server, does not see your 191.168.1.17 address. It sees the address on your router or the address in one of the address pools that are being deployed by your company or by your university. So this was so important because using this, we are able to repeat IP addresses. We can use the same range in different places because they will never meet each other. This was the implementation of NAT, which is very good because it enabled us to use IP version 4 addresses that are already depleted much longer instead of crossing to IPv6, which is what I hate it about. It is the technology that has enabled us to be sustained on IPv4, but also the technology preventing us from enjoying the benefits of IPv6. It's called NAT, but generally, public addresses and private addresses is another type of IP addresses. So we can classify IP addresses based on class, and we have seen that. We have class A addresses, we have class B addresses, class C addresses, class D and class E. Class D and E are out of scope of this class. A, B, and C, we have seen how they work. And then we can also classify them based on scope. Public addresses that can be routed on the public network, public internet, and private addresses that can only be used in private intranets or local area networks. But we also have addresses we like calling special addresses. Addresses like 255.255.255.255, limited broadcast address. An address we send to a packet if we want every host on the local network to receive that packet. We also have the any network IP address, 0.0.0.0. You're going to see this a lot in IP routing, static routing particularly. And even in static routing, particularly the one we call the default route, because we are trying to refer to any IP address, which I'll be using that IP address. Then we have the loopback address. This is why you people are always having 127.0.0.1, calling it the local host. Actually, for your information, even if you use .0.0.2, .0.0.3, .0.0.4, .0.0.5, .0.0.6, .0.0.7, the whole of this is a loopback range. You're only using .1 because that is the one you were taught. And then we have the link local address. We have the link local address. Now, the link local address is a special kind of range. It's a very special kind of range. Later on, we shall talk about DHCP in this class, not today. DHCP is a way that certain servers are able to allocate our computers' IP addresses automatically without our intervention. So we need to get into our computer and tell it that you'll get an IP address automatically through DHCP, so that when we power on our computer, it sends out a DHCP discover packet. However, sometimes we tell our computer that you'll get an IP address automatically through DHCP. It sends out a discover packet, and there is no DHCP server out there. When your computer is told that it will get a DHCP server to allocate an IP address, that computer believes it needs to be able to speak on the local network. When it doesn't find a DHCP server to give it an IP address, it assigns itself an IP address automatically. Yes, you heard me right. It assigns itself an IP address automatically because it needs to be active on the local link. That address is called a link local address, and it will always be in the range 192.168.0.0. So go back home one day, destroy all IP configurations in your computer, run the command ipconfig /release. It will release the IP address your computer got from work or from school, and then it will have no IP address. Then go and configure it to get a DHCP IP address when there is no DHCP server at home and you're not tethering to your laptop, to your phone. Because when you tether to your phone becomes a DHCP server to allocate your laptop an address. But if you don't tether, then your laptop will not get a DHCP server. You will check the IP address of your laptop by running ipconfig in CLI in Windows or ifconfig in Linux, and you will find that it will have allocated itself an IP address in the 169.254 range. It's called a link local address because your computer feels miserable need to communicate on the local link. Are we together?
Excuse me, John.
Yes, please.
I have a question.
Yes.
My question is about two kinds of network. Network A is Wi-Fi of a certain university, and everyone can access it, lecturers and students. Then network B is about network B is Wi-Fi of a given company, and a few members can access it, maybe 5. So which one is a private network and which one is a public network?
Now, both Wi-Fi A and Wi-Fi B are private networks. By private, we don't mean secure. By private, we mean it is in a local area network. When you have Wi-Fi A, and we are going to do this in this class, yes, congratulations, we're going to learn how to configure Wi-Fi using our access controllers and fit access points. When you have Wi-Fi A that has no password, you have simply put there a switch, okay? Put power on it and connected an internet cable that brings internet and left all the ports open. Anyone can bring their laptop and plug in and use internet. That's what you've done. You get it?
Yes.
Yes, the access point somewhere, which is giving the Wi-Fi signals, is open. No one has, you have not put a password. So once someone taps in and connects, they communicate to the internet. What happens? This access point will give them a local area network address, a private address in the private range, typically 192.168.something.something. And you will communicate. It is still a private IP address. And somewhere this AP will be connected to some switch, which will be connected to some router, which router will do NAT when you're speaking to the internet. Are we together? Jackson?
John,
Okay.
I'm getting.
Yes, so both network A, Wi-Fi, which is open, like my UG, and network B, Wi-Fi, which is closed, like your company or your school, both of these are still private networks. That's that one private, it's like having land, it's like having a very big home and very big land, and anyone can enter and play football. It doesn't make it government land, does it?
No.
Hey, it is still private land, but you are allowed to be educated. So even this Wi-Fi, which is open, for example, if you get out of range of your university, you can't use it. It is still private. It is a private network, but it is open for use. Are we together?
Yes.
Okay. Perfect. So I will talk about this slide more when we get to IPv6, the differences between IPv4 and IPv6. But first off, IPv4 has this in its version field, and IPv6 has this in its version field. But there are a lot of differences, and there is a lot of things we are missing because of not moving to IPv6. I've just talked about NAT. So if I happen to access your website, you cannot know it's me who is accessing, because a NAT device is translating my IP address into a public address. You can't know who is the owner of that public address. In fact, these days we have what we call NAT to NAT, or even NAT to NAT to NAT, that some ISPs use, that IANA hates and even sued several people in those other countries for using it. But it is like NATing behind NAT. So we convert the local private address, we convert it to other private addresses again before you convert it to a public address. It's a very bad practice, and it makes it very easy for us to access your networks without you being able to identify us, because we are behind the NAT wall. IPv6 prevents that, because it gives us the original objective of internet connectivity, which was end-to-end connectivity. It is me reaching Hope. It is me reaching Twaha. It is me reaching Shinta. It is me reaching Doreen. It is not, Lab 4 reaching Doreen. No. Because if I'm in Lab 4, there is typically one router that is NATing all traffic for the entire Lab 4, 200 computers, to the same public IP address. It's the one I will see. So I don't know that it is Shinta or Sam or Thomas or Twaha or Dennis or Alfredo or Habiba or Hope or Caroline. I don't know who is accessing my machine. It's a public IP address. If you built a website and checked the records of IP addresses accessing it, and we have like a class like this, and maybe it has 200 people, and they're all accessing that website, you might find that website is being accessed by something like 13 IP addresses, when all the 200 people are logged in, because Airtel and MTN have allocated the same public addresses to most of them, which is not a good thing. It's not a good thing for several reasons. Also, types of addresses, unicast, broadcast, and multicast are supported by IPv4. IPv6 supports unicast, multicast, and anycast. We shall talk about anycast when we talk about IPv6. IPv4 addresses are already used up. We no longer have any other addresses as far as IANA is concerned. They are used up. The remaining addresses are held by Afrinic and a few other regional internet registrars. IPv6 has virtually unlimited. Yes, unlimited virtually, because we actually tend to say, if we allocated an IPv6 address to every grain of sand on this planet, each of them will receive an IP address, because it is some number times 10 to the power 34. It is a very big number, unrealistically big. It has an inappropriate packet header design, and this one has a simplified packet header design that is divided into modules. App dependency induces flooding. We have just seen app, but we shall talk about it more. This one supports automatic IPv6 address location, either by use of DXIPv6 or even stateless auto address configuration.